Hello everyone, I will present a paper about reservoir computing. It's titled Task Adaptive Physical Reservoir Computing. Uh, uh, there's a physical separation between processing and memory units in conventional computer architectures, and it causes energy waste due to repeated accessing of data. Accessing to data is something that uh, the processor is idle and cannot do some processing. That is called von Neumann bottleneck. It's a classical problem for classical computer systems. To prevent this, there's a new type of computing which is called neuromorphic computing. Takes the inspiration from the brain to create energy efficient algorithms and hardware systems. And they capable of doing highly sophisticated tasks. And neuromorphic computers can have millions of artificial neurons and synapses processing different information simultaneously. It's something they have in advance as an advantage. And reservoir computing is also a type of neuromorphic architecture with complex recurrent pathways. It's shown in the figure. There are recurrent pathways in the reservoir, and it provides a highly sophisticated and highly efficient computing force. Neuromorphic architecture maps input data to a high-dimensional space, and then the reservoir they do the computation, and we take a one-dimensional output. Reservoir computing actually originally conceived in software for first time, but the nonlinear and history-dependent response of physical systems can be exploited using the physical reservoirs. It's something that software cannot have. Weights, there are weights for the there's a equation actually for the machine learning systems. There's an equation, and this equation have different variables, and these variables have different weights. Actually, these weights takes input from us, and process this input according to this equation, and outputs us some result. These weights within the reservoir are randomly initialized and fixed actually because of the physical structure of the reservoir. Okay. That is something advantageous actually. We will talk about that later. Physical reservoir computing area is rapidly expanding area actually, with several promising demonstrations. Actually, the optical systems, analog electronic circuits, memory resistors, ferroelectrics, magnetic systems, many. And even a bucket of water, actually. I found a paper about it. For our perspective, skyrmions, topological non-trivial magnetic bursts, they are called, have also been proposed as a host for reservoir computing and experimentally demonstrated many times. I only could find 30 and 35 papers very easily. What are our motivation for actually not the author's motivation for this paper? There is okay, rapid development. Okay, we know that, but there's an outstanding challenge. It's a physical system. Then you cannot change everything whenever you want to. You cannot tune. You cannot reconfigure the system, and this makes reservoir usable for only one task. Actually, one kind of task. Establishing methodology for task adaptive control is a problem. It's the main problem. And they try to solve this issue in this paper. Physical systems have narrow and fixed set of reservoir properties, they say. They have no much room to change. Physical reservoirs, therefore, tends to perform well for one kind of specific task, but poor for others. This is a severe drawback, actually. But for the software reservoir computing, it's simple. You can just change a couple of line of codes, and you have the wanted properties for reservoir. The motivation, they demonstrate task-adaptive reservoir computing using spectral space of physical system that has rich phase-tunable dynamic modes. As a model system of this approach, they use spin resonances of the chiral magnet. They use copper oxide selenide for this experiment. This chiral magnet has different magnetic phases, skyrmion, helical, and conical. They exhibit distinct resonances, and they offer varying reservoir properties and computing performance, obviously. And the beautiful thing about this magnet, it can be reconfigurable and tuned using a magnetic field and temperature. They use magnetic field cycling. I mean, this cycling we will see in a moment. This cycling is just an input for sinusoidal or some kind of a cycling wave, and they send this many times as input and measure the spin wave spectra, spin wave reflection output of the magnet. Each input step efficiently achieve high-dimensional mapping. They find that the thermodynamical metastable skyrmion phase has a strong memory capacity, actually. And this is because of the magnetic field-driven gradual nucleation, they say. It's gradual nucleation. As far as I could understand, its gradual word is important because this provides a phase difference. And this finalizes the memory system. It can be used as a memory. If it's as a memory, it can be tuned as a computer that can predict some tasks, future predictions, that it can make future predictions. But by contrast, the conical phase has modes with great reservoir nonlinearity and complexity, which ideal for transformation tasks. But we want each of them not distinctly, but together. So how can we compile them in a single physical system? They have a scheme for the reservoir computing. The physical reservoir they constructed use the field and temperature dependent spin dynamics. They apply specific sequence of magnetic field inputs and map out spin wave spectra of copper oxide selenide to form a two-dimensional matrix, as you can see here. And then the reservoir matrix is multiplied by a weight vector to produce an individual output for each input, as you can see here. And they use also ridge regression for the optimization of the output for each task with training data. Ridge regression, by the way, is a statistical regularization technique. It corrects for overfitting, actually. I mean, it's not always good for fitting some data. Sometimes you have to prevent overfitting for the generalization aim. So, ridge regression uses a penalization term, and using this term, it shrinks the coefficients of generalization ability. For generalization ability, the copper oxide selenide has rich phase diagram, offers multiple magnetic textual phases, including thermodynamic metastable skyrmion phase, helical and conical phases, which are easily adjustable by a magnetic field and temperature. To measure the microwave reflection spectra, recording and frequency channels. Here we can see NNM and frequency channels as output and input and many inputs. Between these outputs, the differences between 1 and 6 gigahertz for each field cycle, where chi here represents magnetic field susceptibility for each input and corresponding a frequency output. Okay. Experimental setup. I want to talk about the experimental setup. There's a polished shaped copper oxide selenite crystal, dimensions with 1.9, 1.4, and 0.3 millimeters, in a waveguide with 100 surface facing down. It sits on a copper cold finger of a closed cycle helium cryostat. Apply an external magnetic field, of course, along 100 crystallographic direction, and with a VNA, vector network analyzer, is employed to measure the spectral response of chiral magnetic crystals using fMR. The microwave reflection, here microwave reflection coefficient shown here S11, is recorded by the VNA as a function of microwave frequency to characterize the spectral response for a given magnetic field and temperatures. For our measurements, we sweep the frequency comprising 1601 frequency points at 0 decibel milliwatts applied microwave power. With this single row spectral recording of microwave reflection coefficient of 16 and 1 points, 1601 points associated with the frequency dependence of the dynamic magnetic susceptibility. The input layers, sequential magnetic field values are inputted for our reservoir. Projecting a given input, we have an input function and we make it a magnetic field projection and apply it to the reservoir. Each field cycle N starts with a low magnetic field, as it is in here, and increasing to a high magnetic field, comes back to a new low. Then it's a one cycle. Their separation is shown as a H range over 2. And we have a center magnetic field value. For the transformation task, the input function is a sine curve and encoded over 100 field cycles. Our forecasting tasks use a chaotic oscillatory Mackey glass time series, and in the last presentation, Mejit told us about these these series. Figure 1 shows here. Figure C shows spectral output of our reservoir in response to input time series dataset, and the 70% of this data for training and 30% of this data for testing. We feed the reservoir with the 1,000 data, for example, 700 data outputs used for training for the target function, and then with the 30% of the output used as a testing output. Here we see physical reservoirs attempt shown in a blue line, and red dotted is the actual output as expected. It's actually remarkable results. It fits perfectly well. And it is actually in here, we have Mackey glass series. We have an input, but the reservoir outputs to 10 steps ahead. It's actually forecasting and predicting the future signal. It has remarkable results. And the right panel shows nonlinear transformation. Here we have also great results, but they actually used here different phase of reservoir. What can I say? MSE values, mean square error values, are very low. And by the way, the gray lines here, the result of prediction. It's actually also a prediction, and it is done without reservoir, and its error rate is very, very high. So we can see that reservoirs work perfect for prediction and also transformation tasks. Here the phase tunable nature is used for this reservoir mode changing for different tasks. This reservoir computing has rich magnetic phase diagram because we used copper oxide selenide. Metastable skyrmion phase can be generated at low temperature, below 35 Kelvin here, and using some techniques that they don't actually explain in detail. They're called quenching techniques or field cycling protocols, but they don't actually explain in detail. Here, figure B, and dependence of the spectra, we can see its temperature is held at 4 Kelvin, magnetic field at 60 millitesla, and we can see phase differences throughout the field cycling changes. For when the cycling number is 100, just 100 input data is sent, a sharp peak we can see around 4 gigahertz, corresponding to actually low energy spin wave modes of the thermodynamically stable conical phase. The conical mode amplitude shrinks as we apply the cycles, and the conical mode amplitude shrinks, and the skyrmion modes appear around 2 and 3 gigahertz, as highlighted by the gray lines here. The skyrmion modes are identified at 4K and 15K. Here we can see from this plot, and they disappear for higher temperatures at 25K and 35K, where the spectra are dominated mainly with conical phase. As the cycling proceeds, we can see the phase changes in this figure, and yes, this figure. Here with the figure B, C, and D, different magnetic field values, we can demonstrate the different phases. Here we can see conical. Here we have a hybrid conical and skyrmion, and it's a helical. And this demonstrates the tunability of the magnetic phases for our reservoir computing. I want to talk about magnetic phase of the crystal. For small magnetic fields, spins in copper ionized by 2 ions point as spiral rotation within a specific plane, as it's seen here. Hence, and then having the corresponding shape, it's helical. When the magnetic field is increased, the finite spin component along the field direction for each copper ion, forming the conical state skyrmion phases, and then below the Curie temperature, high temperature pockets close below the Curie temperature, we can see the skyrmions. In this paper, skyrmion at low temperature, a distinctive thermodynamically metastable skyrmions can also be realized at low temperature, actually. And in this paper, we can see that lower temperatures. And their population can be controlled by the number of field cycling, making them an adequate candidate to perform reservoir computing. Figure A to see reservoir performance. We can compare the reservoir's performance on different tasks using magnetic phases of skyrmion, skyrmion conical hybrid phase, and the conical modes at 4K, 4 Kelvin, with magnetic fields range of 90 millitesla. And notice that only 300 we apply 1000 field cycle, but we can only see the 300 of it because it's for testing. The rest was for the training. We should remember that the forecasting, the system is trained to predict the future behavior of a Mackey glass signal 10 steps ahead. The reservoir performance is evaluated qualitatively here using the mean square error, and it's very low. Actually, it's seen easily. But if you compare these different phase performances, we can see that it's the best for the conical phase cannot accomplish the forecasting task, but skyrmion actually accomplishes very well. In the figure B, we can see transformation task. Skyrmion does very well, actually. It's enough actually, maybe. But conical phase does, when the magnet is in the conical phase, it does way better. Okay. Okay, what can else? Okay. The prediction performance deteriorates and mean square error increases at the conical. And we can see by setting magnetic field to 98, we can have hybrid type of hybrid type phase for the magnet, and its hybrid reservoir were better than the both skyrmion and conical modes in both tasks, actually. Here we have the upper and lower whiskers. Here, upper and lower whiskers represent maximum and minimum magnetic field values in the cycling scheme, respectively. The height of the box represents H range, and the central line for the center. Initial side, there is a cycling from bottom to up for these plots. Gradually moves up, means at the bottom at the lower whisker, and gradually moves up and down as a function of n. The strongest performance is found when the field cycling lies entirely inside the skyrmion phase at lower temperatures. The performance gradually worsens as the field cycling moves beyond the skyrmion phase and is reduced dramatically when leaving the skyrmion phase at high temperatures. This excellent forecasting performance of the skyrmion reservoir is highly correlated with its memory capacity, actually. In figure F, where variation of H range for 7 to 3 millitesla, it is clear for all measured temperatures that larger H range values provide optimal reservoir performance. And in figure G, deeper into the helical phase, as it goes to the helical phase more, they perform far more poorly, whereas the optimal performance for the transformation task is demonstrated when the reservoir is in the conical phase, that because of this strong nonlinearity and complexity features. Figure 80C shows a spectral evolution of different magnetic phases with field cycling. The high transformation performance of the conical phase can be seen in here, this spectral with the spectral output, because we can see the huge shift with the input as a response to the input field amplitude. The dispersion curve of the helical phase displays a flat profile that doesn't have a response much, and this is why it cannot do the transformation task very well. It has a poor computational performance. Peak position shifting very weakly. At the much higher amplitude, frequency shifts are found in the highly performing conical and skyrmion phases, producing strong nonlinearity. And therefore, they have low mean square error in the transformation tasks. The origin of the great performance of the skyrmion reservoir for forecasting task can be explained by comparing A and D points. The spectra of both helical and conical phases are identical across the point A and D. As you can see, A and D points are at the same with the input value. They take the input, they output according to input and nothing else. But if you look at the skyrmion phase, we see that different response, and this because of the memory property of the skyrmion phase. But conical and helical phases doesn't have they lack of memory property. Okay. Okay. Actually, I mean, the skyrmions are affected by the past inputs, and this proves their memory property. So we have reservoir metrics here. These metrics define the reservoir performances. We have nonlinearity. This metric evaluates the ability of the reservoir to predict the true readout Km and FMR frequency channels when shown up the 8 previous inputs. We have a formula here. It's a correlation coefficient with the future prediction, and the difference between future prediction and the current input, and we have the nonlinearity coefficient. VM memory capacity determines the reservoir's capacity to remember previous information about its inputs. And the formula are actually same. We find the average differences between the data points, but this time it's because of it's with the past inputs instead of the future prediction. We found then memory capacity value for the reservoir, and we have complexity determines the effective latent space of the reservoir, the amount of information encoded in the spectra. They don't have much detail about it, and I found this information actually from the supplementary file and different places, from different places. We have plots and Spearman's rank correlation coefficient table here. Nonlinearity, memory capacity, and complexity, we have those metrics. it is clear that memory capacity metric shows similar behavior to the performance of forecasting MSE here with the forecasting performance, and memory capacity decreases with the applied magnetic field. It suggests that memory capacity is a key property for a better performance in forecasting tasks. Memory capacity in the skyrmion phase stems from the history-dependent fading memory property generated by its gradual skyrmion nucleation with repeated field cycles. Rich and complex spin wave mode. Rich and complex spin wave mode dispersion in the conical phases provides the physical basis for the high nonlinearity and complexity scores. And it offers a strong transformation task performance. We have the algorithm outputs from -1 to 1. 1 corresponds to perfect proportionality, of course, and the -1 for inverse proportionality, and 0 denotes no correlation. And negative MSE meaning better performance. The performance for forecasting strongly correlates with the memory capacity, as we can see from the here. Here with the -0.89, and the complexity 0.57 here. Okay, revealing that memory capacity is favored and complexity is disfavored for the particular types of tasks. While the opposite is true for transformation tasks, it's important actually highlight that memory capacity and the complexity have a clear negative correlation, indicating a trade-off nature between these two reservoir properties. And then high correlation between nonlinearity and complexity suggests a more nonlinear system enhances the amount of meaningful input data encoded in the reservoir. And to display high complexity relationship between the reservoir performance evaluated evaluated by the mean square error. The metrics for this skyrmion phase appear to be clustered here. It's shown with the blue. And it's actually distinctive property for this type of reservoir. Clustered at the high values of memory capacity between 4 and 7, and that confirms that skyrmion reservoirs memory is responsible actually for the great forecasting performance. And by contrast, system's ability to perform transformation tasks reaches its full potential by maximizing the complexity. Here we have very, very low square error here, which for the conical phase, of course. I think that's all for this presentation. Thank you for listening.